Here we are going to talk about the database structures and access methods. So earlier we talked about the requirements for a spatial database management system, including the data type and including the spatial operations, and also some access methods for the geospatial data. But however, in these units, we are mainly going to focus on the spatial access methods or spatial indexes. So the data types for the geospatial data and also how the operations for the geospatial data and how does it represented is in the different spatial database management system. That is actually something I'm not going to talk about in this unit. So if you are interested in those, you can say those information, you are encouraged to find some material online. So here we are going to talk about what defines the performance of a database query. So in order to talk about that, we are going to discuss the database structures and also their general access methods. So first of all, a typical database organization to organize the data is by collection of tables, and then those tables contains the records of attributes, and then those information they are stored on a set of disks, and or what we call the hard drive or hard disks. Then in this case, the time to find the data that we want on the hard disk it's actually composed by a few steps. And so basically, every time when we want to read some information from the hard drive, that is the time we say the input and output or I/O. So usually, database query, the most time-consuming part is the input and output. So usually, as you can see, what we said over here, the time taken to transfer a data unit. So every time when we are reading some information from the hard disk is by different data unit, or the other term to call the data unit is the data block. So which means that every time each of the I/O we are reading or writing a data block from the data disk, from the hard drive or hard disk, or to a hard drive or hard disk. And then the time taken to do that, it has three components or three steps. The first step is the seek time, or is the seek time. So the hard disk is kind of like a disk, and then in order to write to the disk or read from the disk, there is a mechanical movement of the disk head. So there's the movement that you need to do for the disk head to go through across the different tracks on that disk. So you can imagine it's kind of like the DVD or CD. There's a disk head to read from different tracks on the disk. And so, in order to move from track to track, the disk head needs to move mechanically from across different track. So this is the time spent for this mechanical movement is called the seek time, and usually is also one of the most time consuming step. And after the disk head has been moved to the correct track, then there's something called the latency, which is about rotating the disk to the correct position. So on that track, so right now the disk head has been moved to the correct track, but however the disk is like the round disk. So in this case, you need to rotate the disk to the correct position so that you are going to read from that, starting from that position to like a disk block. So the rotation to the correct position is called latency. And then finally is the CPU transfer time. That CPU transfer time means that after the diskette is in position, then it's going to read a certain data block from the disk, and then you need to transfer that disk block into the CPU or into the memory. So that transfer time is also one of the step that you need to take. So in total, to read information from the hard disk, you need to take the seek time and latency, and also the CPU transfer time. And so, how your data is physically organized or managed in your on your hard drive or on your hard disk, it actually will result in a very different performance when you are trying to read a file or information from your hard drive. So, just for example, if the information that you need locates on different tracks, then in this case, you may need to have a lot of seek time, and your disk head needs to go through different tracks to read different data blocks, and then compose them together. Then becomes the one entire information that you need. Then in this case, that types of organization of the information on your hard disk is not a very good organization, or not a good structure. So usually, if it's like atomic information, then in this case, if they are the information of those of those data blocks are organized sequentially on the same track, or very nearby tracks, then in this case, the I/O time spent is will be, you can say, will be reduced, so that's the I/O time will be faster. So as you can imagine, so how to organize those information on your hard disk actually result in a very different query performance. So here we are going to talk about, based on that information that we just mentioned, we are going to talk about two types of database structures, and also their access methods. So these two are the famous two. First one is the unordered table with the linear search, and then the other one is the ordered table with the binary search. So let's talk about the unordered table first. The unordered table, according to its name, which means that the data that you managed in that table, it's not ordered, and by any information, you can say by any attributes, it's not ordered, and so usually it's insert to the records are inserted into the table according to the entry order. So the new one, the new one will be on the top, and then the older one will be on the top, and the newer one will come at the bottom. So it's kind of like it's the although it's called unordered table, but basically it's kind of like ordered by its entry time. So the meaning of the unordered table is like the records in this table is not ordered by any attributes, by any information of the attributes. So basically, the new records are inserted into the table in the next physical position on the disk. So you can imagine that you have a disk, and then the record that you start inserted is on one specific location on this track. Then in this case, after you write a certain information, and the new records comes in, and then you write the next one, and the new record comes in, and you write the next one. So it's kind of like they are put sequentially side by side with each other on that track. Okay, so that's the meaning of this type of structure. So the good thing about this type of structure is that the insertion of the new record is very efficient. The insertion of this type of record is very efficient because when the new record comes in, they just need to continue the writing on this on this track. So the insertion is efficient. So like I said, but however, in this case, no table structure beside the entry order is maintained in this table or in this, you can say, in the physical position of those records on the disk. So just for example, this is a table of the weather data. So the first attribute is the ID station, is the ID of the station, and the second attribute is the temperature reading, so in the Celsius, and then the third attribute is the time of those readings, and so that because this is not entirely because this is not entirely this is an older table, so which means that the new records comes at the bottom, so the older one will be on the top. So this is basically the an older table, but however, as you can see, because it's sensor reading, so although it kind of like seems like the data is ordered according to the time, but however, it could you could also insert some historical data as well. Okay, so it's not guaranteed that the data is ordered according to the time. Okay, so this is just an example of the unordered table. So based on this unordered table, so if we are going to query some data from this table, so for example, if we want to retrieve the records that has the temperature higher than 21 degree. Alright, so which means that we want to find all the records that has the that satisfy the temperature reading that is higher than 21 degree. So as we can see from this table, we have those two readings that those two records satisfy this condition. So the answer that we want is these two, the third and fourth one. But as you can see, this table, the entire table, is unordered. So in order to find in order to find the records, so all the records needs to be retrieved and compared to the condition, the search condition to answer this query. So which means that we need to go through each of the record one by one, and then to determine whether this record fits with the criteria, whether the next record fits with the criteria, whether the next one and next one and next one fit with the criteria. So you need to go over all the records on this table to finally answer the query. And this type of search is called the linear search. This type of search is called the linear search. So here is one way to represent this type of the performance of this query. As you can see, here is the what we call the big O notation. This is O, so this is what we call the big O notation. So this type of notation is used to describe the computation complexity or time complexity. So the meaning for this time complexity is about a way to represent the worst case scenario performance of this algorithm. So right now the algorithm that we are trying to represent is the linear search. So for the worst case scenario to answer this to execute this linear search, the worst case is that we need to go over everything. We need to go over all the records to answer the query or to answer these to execute this algorithm. So the O of n, this big O notation, O of n, means that the n represents the number of data records that you have. So which means that the time complexity of executing this linear search it require the number of it require the execution proportional to the number of data that you have. So, which means that the performance is proportional to the n, to the number of the data records. So the more data that you have, the more time that you need to take to answer this linear search, and their their relationship is the O of n. So, or you can say it's like kind of like one by one increasing of the execution time. Okay, so which means that, or the other way to represent it, to talk about it, is like if go over one record, if you only have one record in your data table, then you need to spend 1 unit time. Then if right now you have n records in the data table, then you need to spend n unit time. So that's the representation for this O of n. This is the representation of this O of n. Okay, so on the other hand, if we take a look at the ordered table, so in the ordered table organization, then each record is inserted into the table in the order of value that according to one or more fields. Okay, so those fields they are called the ordering fields. So when you insert new records to this table, then you need to first consider where exactly that this record needs to be inserted into on the hard drive, on the hard disk. So just for as an example, this table is exactly the same table as the previous one, but however, the way that they are organized on the hard drive, on the hard disk, is ordered by the temperature. So as you can see, right now let's just imagine the order over here represent their order on the hard disk. So the first record is comes as the first position, and followed by the second record, and followed by the third one, and followed by the fourth one, and so on and so forth. So the physical position of those records are ordered by the temperature. So from the smaller temperature to the lower temperature to the higher temperature. So in this case, the one of the problem to maintain this ordered table is that the insertion of the new record can be expensive. So just as an example, if right now I have a new record that the temperature is 21, then first of all I need to find out where exactly should we insert that record to. So for example, the temperature 21, it needs to be inserted over here. Then in this case, originally the temperature 22 record is just directly followed after these 20 records over here. Then it needs to be moved to the next position, and then we need to insert the 21 record over here. So the insertion of the new record could be expensive in order to maintain this ordered table organization. So if the insertion is time-consuming, then what's the benefit of doing such thing of maintaining this ordered table? So the benefits, or you can say the greatest advantage of having an ordered table, is the binary search on the ordering fields. Alright, so the binary search can be only executed on the ordered field. So, for example, let's execute the same query, which is the retrieval of the records that has temperature higher than 21 degree. Then in this case, the previous one, the unordered table, we need to go through everything, go through all the records to answer this query. But however, right now, the to answer this query, we can perform what we call the binary search. So the most efficient way of course, one of the efficient way to answer this query is starting from the middle one. Is starting from the middle records. So supposedly that we know there are 5 records over here. Then just let's directly go to the middle one, and then the middle record over here, and then so we can retrieve this disk block over here. We can retrieve these records from you can say this is one I/O. So we have one input output over here, and then we read these records, and then we can compare whether this record satisfy the query condition or not. So as you can see, 20 is smaller than 21. So which means that right now the information we know is because this is an ordered table. So we know that whatever above above this record, they are all smaller than 20. Alright, they are all smaller than 20. Then in this case, if they are smaller than 20, of course they are smaller than 21. So the first half of the record, they are not necessary to be retrieved to compare with the query result. So the answer that we want will be you can say on the second half of the records. So what we can do next is we don't know what's the distribution of the record distribution of the values over here. So what we can do next is we can go to the half of the second half. Alright, we can go to the half of the second half. So in this case, as we can see, we can go to the next one over here. So and we can have another disk block query, disk block reading from the hard disk. Then we can find out, okay, say 22 is higher than 21. And right now, we know that all the readings below this record they all satisfy this query condition. So we don't need to go to this final data record to determine whether it satisfies the 21 query criteria or not. So automatically, we know that these 23 satisfy this data record satisfy the query condition. So if there is any other like data records between these 20 reading record and 22 reading record, then the next thing what we are going to do is we can go to the half of the records in between these two records, and then try to determine whether that satisfy the result, satisfy the query condition or not. And so on and so forth, we can finally find all the records that satisfy the query condition. So as you can see, this type of this type of search algorithm is very different from the linear search. That is to go through the records one by one. So this type of search is what we call the binary search. So every time we just eliminate half of the remaining uncertain data. So for example, like the first we cut the records into half, and then we eliminate half of the records, and or eliminate, or you can say decide half of the record whether they satisfy or they do not satisfy the query condition. So in this case, as you can see, every time we go to half and half and half, so the time complexity of the binary search is O of log n. Right, O of log n. So because every time we just go to half and half and half, so the performance is to the log of the number of the records, right? To the log of the number of records. Okay, so that's why the binary search is much more efficient than the linear search, especially if you have a larger and larger number of records on your table. Okay, so that's a famous, you can say, comparison between the linear search and binary search.